as well as the emerging technologies being used to mitigate them. We are a student-led energy club focused on ideas that support key steps for a clean energy system. Plus, through our platform, we provide opportunities for undergraduate and graduate students to get involved in research and energy, technologies, and policy through our mentorship program. For the NC State students in the audience today, if you're interested in joining our organization, we have 5 officer positions open, and you can find more details on our website at ncsuenergyclub.org. Now, I would like to briefly introduce our panelist, Dr. Destenie Nock. Dr. Nock is an assistant professor in civil and environmental engineering and engineering and public policy. Her research is focused on applying optimization and decision analysis tools to evaluate the sustainability, equity, and reliability of power systems in the US and sub-Saharan Africa. We will have a brief Q&A after Dr. Nock's webinar, and we ask that you please use the Q&A tab on the portal to ask your questions. So I'm going to now pass it on to Dr. Nock.
Thank you very much, Martina. So in this talk, I am going to talk to you about a method that I have been using to evaluate energy transitions in terms of sustainability and equality objectives. So just to get a sense of who's in the audience and what you guys think about, I would like you to type in the chat what 1 to 2 words you think of when you hear sustainable energy transitions. And you have 15 seconds to do that. So the pressure is on. Plus I can't see anybody, so I can't see if anybody's actually typing. Okay, we have 1. Anybody else awake out there in the Internet of Things? Okay, so I'm seeing solar, smart grids, wind farms. I'm seeing specific technology types and CCS. Less fossil fuels has come up multiple times. Long-lasting and economically feasible. I see cost-benefit analysis. Okay, and the 15 seconds is up. So you guys can keep putting in the chat if somebody didn't answer. But one of the things that I think about are trade-offs. So for me, every sustainable energy transition is going to have a trade-off, right? You're going to want to develop your grid so that it's long-lasting. You want the environmental sustainability. That's a lot of times what I hear people talk about with the renewables and moving away from fossil fuels. A lot of times that's the sustainability piece of less air pollution emissions, less water use, etc. And then now in the public view, we're thinking a lot about the equality concerns of sustainable energy transitions, because without focusing on equality, we might end up making social imbalance much worse if we are only reducing air pollution emissions, let's say in like the wealthiest areas in the United States or in other parts of the world. So given that most of you all mentioned long-lasting and specific technologies that are viewed as low pollution, we're going to start the talk in the bottom half of the triangle, and then the second half we'll talk about the equality. So this is a paper that I wrote as a part of my PhD, looking at how you can think about a holistic view of sustainability. It's set in the context of the New England power system, and it's really focusing on how do you look at and measure sustainability trade-offs. So in case you don't know where New England is, it's in the upper northeast quadrant of the United States. It's made up of Maine, Vermont, New Hampshire, Massachusetts, Rhode Island, and Connecticut. And New England has a ton of changes going on right now. Even though the US had left the Paris Climate Change Agreement, New England had agreed to stick with the plans. So they are retiring at least 4.2 gigawatts of coal capacity, and they have, well, actually, sorry, it's 5.5 gigawatts of coal capacity and oil capacity are at risk for retirement. There's uncertainty around the 3.3 gigawatts of the region's nuclear power plants due to risk concerns there. They're also really pushing for offshore wind. So there's a lot of changes going on. And one of the things that people have been asking is, well, which technology is the most sustainable? Okay, so if you close your chat, you should open it again. And out of these 4 technologies, so we have a natural gas plant at the top, solar panels, a wind turbine, and a hydro plant. Which one would you say is the most sustainable? Okay, I'm going to give 15 seconds again. We got this. 1 for solar. Okay. So I see mostly hydropower because it doesn't require peaking plants. Thank you for the explanation. Depends on resources in the area. Very smart cookie right there. Depends. Yeah, so I agree, it does depend. But if somebody was to say which one was the most sustainable and you had to choose, I definitely see most people either choosing solar, wind, or hydro, and we can all agree, okay, natural gas is probably not the most sustainable in terms of like environmental sustainability, et cetera, when we look at technology individually. So now we have to make the question much harder, right? Because most people could give us an answer. So we have number 1 on the, let's see, it's the left, which is half, it's like a 50% natural gas, 50% solar. And then on the right, we have a 50% natural gas, 50% wind. So in the chat, if you could tell me left or right, which one you think, which combination is going to be the most sustainable? All right, so I'm seeing almost even between left and right. Nadia said it still depends on the area. That's very true. It does. So the thing is, when we're thinking about the combinations, it's really difficult for us just by looking at these technologies to know which one's going to have less air pollution emissions. Is wind or solar going to require more cycling? Which one can scale better? That type of thing. So just some of the sustainability concerns that I think about with these different technologies. So solar and wind have the scalability and variability concerns. Also with like rooftop solar, for example, and community wind, there are unequal adoption rates between different communities due to large upfront costs of these technologies. So then, of course, like with natural gas, we have air pollution. We also have like methane emissions concerns and like pipeline laying concerns. And then with hydropower, we have a lot of drought and water use concerns. There's also a lot of concerns about fish. One thing that I learned through doing this project was that in Connecticut, the hydropower plant that is, I guess, the largest one in the New England region, it uses the river as its lower reservoir. So when it wants to store energy, it pumps it up to its lake. And then when it wants to create electricity, it reduces water from the lake through a turbine down to the river. And so one challenge that we find in New England is that sometimes when we want to store a lot of electricity and we're pumping up from the river, we actually end up reversing the flow of the river. And that causes a lot of problems for fish. As you can imagine, they get really confused because nature's not supposed to do that. So in a nutshell, everything has trade-offs. So some previous literature talked about the single technology. So Maxim 2013 had looked at 14 technologies across 10 different sustainability indicators in a global context. Klein and Whaley looked at 13 electricity options across 8 different decision maker preference scenarios from the US. And one thing that Klein and Whaley found was that biopower and geothermal scored the highest in terms of their different sustainability metrics. But what we kind of viewed as a limitation of this work was that an electricity system will never just be one technology at a time due to reliability concerns, security concerns, etc. So the sustainability of the whole system does not necessarily equal the sustainability of the parts. So now we kind of get to my main research objective in this first part, which was to create a model that can capture the interactions between different technologies. So I really view the electricity system as a resource adequacy problem. The first thing that we need to do is make sure that no matter which combination of power plants we have on the grid, we have enough to meet our consumers' electricity demand. So in the future, all these different power plants will change, but you'll probably have some sort of combination of hydro, nuclear, solar, wind for the foreseeable future, and then natural gas and oil plants as well. And we just wanted to make sure that whatever scenario we were testing for the different combinations of power plants, we had enough to satisfy that electricity demand. So in this first model, we actually did not include transmission constraints, meaning that it's an unconstrained network. So we're assuming that there's no congestion, meaning that electrons can freely flow from the plant to the consumers. Okay, so here is the overall methodology for ranking different systems. First, we take in an hourly demand, renewable resources, so that's like solar, radiation levels, wind speeds around the region, nuclear outage data, and we also have some natural gas pipeline information in here. We put in some initial generation capacity levels just to kind of start the model somewhere. Then we run this through our electricity model simulation, which I'm going to explain on the next slide. We keep running it to see if the portfolio can reliably meet all of the electricity demand across a 5-year time period in our model. If the portfolio is not reliable, then we say, okay, we need to add capacity and build more power plants, and then we'll rerun the electricity model to see if it can actually become reliable. And then once we have a reliable portfolio, we output the energy by source. So how much electricity did the power plant generate over that 5-year time period? We'll calculate the sustainability metrics, and then we have some preference scenarios that we use to represent different stakeholders, and then we will rank the portfolios based on those different stakeholders in the model. I know it's a lot to take in, but basically the green is defining electricity portfolios, and the yellow is evaluating the sustainability of the different combinations of power plants. So this is our initial electricity model. We start at time t with our hourly demand, which is HD here. We dispatch nuclear first due to historical costs of electricity. Then if there's still demand left, we dispatch solar and onshore wind. If there's, we check again if there's demand left, then we would go for offshore wind. And if there's still demand after that, we dispatch natural gas and hydro based on the historical dispatch levels in the New England region. Because in New England, the natural gas pipeline is a really big concern, we have to check and see if our pipeline is maxed out after we dispatch natural gas and hydro. If the pipeline is maxed out, then we assume that we're in winter because natural gas would go to the heating sector first. And so a lot of times the heating sector would push it up and mean that we can't just use natural gas anymore for electricity. So if it is maxed out, we assume we're in winter, and we would dispatch oil first, followed by hydro, because the river for hydro needs to stay higher in the winter, so that's why we have to go last. If the pipeline's not maxed out, we assume that we're in the summer, and so then we can dispatch hydro first, followed by natural gas, followed by oil. And if after all of this, we still have demand left after we dispatched all of our technologies, we say we need capacity, and that portfolio is taken out of the model, and we'll go back and we'll add more, and then we'll rerun. So this is run for all hours of a year for 5 years. And so it has to be reliable across a wide range of different electricity demand profiles. So after we run the model, we get these outputs. So the each different bar grouping represents a different portfolio or a different combination of power plants. The solid bars will relate to the capacity, which is the left side of the graph, and the fuzzy bars or the striped bars connect to the energy contribution of those different technologies, which is on the right-hand side of the graph. The green is offshore wind, yellow is solar, brown is natural gas, blue is hydro, gray is oil, and red is nuclear. So one of the things that we can do with this model are kind of ask some questions like, what is the role of nuclear in sustainability in the New England region? So you'll see that portfolios 1, 2, and 3 have no nuclear capacity in them, and portfolios 4 and 5 have actually increased the level of nuclear relative to the base case in portfolio 0. Another thing that we can ask is, which generation should we use to support high offshore wind penetration in the New England region? So portfolios 1, 6, and 8 through 10 have a really high level of offshore wind for the region, so that's at 10 gigawatts. And then portfolios 2 and 7 have a medium level of offshore wind at about 6 gigawatts, and that's like relative to our base case in portfolio 0. So our sustainability model is a multi-criteria decision analysis model, or MCDA model. And these are the steps for doing an MCDA. First, you need to identify your alternatives and your sustainability criteria. So the alternatives are going to be the different portfolios that I just showed you in the bar chart. And the sustainability criteria I'm going to talk about on the next slide. Then we need to calculate the criteria scores based on the projected energy contribution. So those would be our sustainability scores. Then the third step is to normalize that criteria between 0 and 1, just so that we can compare across different units of measure. Then step 4 is going to be to assign preference weights, and that is going to represent the relative weight of importance of each sustainability criterion compared to others. So this is just to get a sense of, if we have different people with different preferences, how would they trade off different portfolios? And then step 5 is going to be ranking those different alternatives. So this is the sustainability criteria that we started with. For the economic sector, we have the levelized cost of electricity. In the environmental space, we have life cycle greenhouse gas emissions, air pollution emissions, land use, and water use. And then for our social criterion, we have the fatalities per gigawatt and jobs as a full-time equivalent. To determine the portfolio scores, this was our method of converting the literature survey values into their fixed and variable components. So the ZIJ tau is going to be the raw sustainability score for portfolio J on sustainability criteria, for portfolio I for sustainability criteria J and technology tau. So the fixed sustainability value, so FJ tau, is going to be the sustainability impacts just from building the plant, right? The plant's just sitting there. It has like sustainability impacts from construction. You know, there's going to be jobs created just because the plant exists and there's a town around the plant, and that type of thing. Then the BJ tau, that's the variable sustainability impact. So that's going to come from actually operating the power plant, right? So as an example, this would be like natural gas and oil. You have some air pollution emissions that are associated with operating that power plant. With solar and wind, you're not going to have variable emissions from operating the plants, but there are emissions associated with actually building those technologies. And then the ZIJ is the combination for all the different technologies. So when we normalize the scores, this is our method there. It's the normalized score is XIJ, and when we prefer the maximum sustainability, so like you kind of think bigger is better, more is better, that would be like more jobs is better. So then we would use this equation on the left, where we have the raw sustainability score minus the minimum over the max minus the min, and that would be the maximum possible benefits we get for our group of portfolios, and then the min is the minimum possible. And then for if X min is preferred, that's just lower is better, so that would be like air pollution emissions, you know, and especially in like California, for example, low water consumption would be better because they're really concerned about droughts. And then to turn these normalized scores into a portfolio score, we take the weights. So that would be how much each decision maker cares about the different criterion. And then we times it by the normalized score matrix, and that gives us our portfolio scores, which are the Ys. So to kind of take this to the, you know, the graphs, which everybody loves, we have a sustainability normalized score bar chart here. The portfolios are along the y-axis, along the x-axis are sustainability score. Longer the bar, the better it is in terms of sustainability. The light purple is the cost, the LCOE. The red and green are greenhouse gas emissions and air pollution emissions. Purple is land use. Purple's land use. Blue is water consumption. Orange is fatalities. Black is jobs. And the red striped bar is how these scores will change when you include nuclear aversion. So the red stripe bar is just saying, if we have somebody that just hates nuclear, like all they want to do is get rid of nuclear and that's all they care about, and they want to include that, how would the scores change? So one thing that we notice is that for portfolios 6 through 10, they're all in the top 6, and those are all of our high offshore wind portfolios. Then with portfolio 4, that's our high nuclear portfolio, and it does really well when we don't include nuclear aversion, but as soon as we include nuclear aversion, portfolio 4 will drop from the second best to like the 6th. And then the portfolios without any nuclear, that's portfolios 1 through 1, 2, and 3. Those ones are all in the bottom half of our portfolio ranking, and that's because to compensate for no nuclear, we have added in more natural gas. We've had to deploy a lot more solar and wind, and so there are some associated emissions with that. One thing to note is that because I've given every criteria an equal weight, because we have more environmental criteria, that inherently gives the environmental section a higher value. So that's why we are seeing a lot of the air pollution portfolios that reduce it, like with deploying offshore wind, rank higher. So one of the, and the only time portfolio 9 outranks portfolio 6 outranks portfolio 9 is when we have a really high nuclear capital cost, or we lower our natural gas pollution emissions. So portfolio 6 had high offshore wind without increasing nuclear, and portfolio 9 had high offshore wind and nuclear. So this is when the portfolio rankings would shift. But even then, since portfolio 9 still has nuclear in it, we can kind of use this as a result to say that the region should look at retiring their oil plants before their nuclear plants due to the additional air pollution savings in the region. So I talked a lot about preferences. This is a table of different preference weights that we took from the literature to get a sense about how our portfolio rankings would change under different people's preferences. So the equal weight preference, which I showed you before, is at the top. Then we have like a climate change preference. So that means that here with this 0.9, the person cares 90% about greenhouse gas emissions, and then they just care a little bit about everything else. In the environmental section, they give equal weights to the environmental criteria, which are greenhouse gas emissions through water, and then they give a little weight to everything else. So the bold numbers are just representing where do people really put the weights of what they care about, and then the non-bolded numbers are kind of like small preferences for other things. So here, once we included these preferences, we actually went from 14 portfolios and we reduced them down to a non-dominated set of just 7 portfolios. So that means when we include all these preferences, we can actually eliminate a lot of the portfolios. In total, I actually tested about 35 portfolios, but for presentation purposes, 35 was way too many for anybody to get anything useful out of it. So we see in this equal weight how the portfolio is ranked just in terms of the equalness from the bar chart that I showed you before. And now we can see how those rankings change across these different preferences. So portfolio 9 was our highest ranked portfolio before, and portfolio 4 was our high nuclear portfolio. So we can actually see that the trade-offs that we're getting between these two are they're actually just flip-flopping a lot between like best and worst. But when we really just care about the economy, which is this EC, portfolio 9 ranks really low, and that's because of the high cost of nuclear combined with the high cost of offshore wind. So this would actually, in theory, decrease in the future as the cost of offshore wind comes down. That would be something to take into account. We see that our non-nuclear portfolios are non-dominated. They're at the bottom of our 7, so they're not the best in terms of like any one criteria, but we can't eliminate them because of how well they do in terms of the economy and also in jobs creation. So you might say, well, there are some people that aren't going to care about all 7. Maybe they just care about 2 criteria at a time. So what you're seeing in front of you is called a scatter plot matrix. And this is for comparing pairwise comparisons of sustainability criteria. So how we would read this is, let's say we only cared about air pollution and land use, and we didn't care about anything else. Then you would look at the intersecting box between these 2. And that just tells you the trade-off that you're going to get when you move from portfolios that are like where you only care about air pollution and you care about land use. So the red dot represents portfolio 9, which was our most sustainable portfolio when we looked at everything equally. And so you can actually see that when you're doing these pairwise comparisons, it's actually bouncing around a lot. When we look at some of these, we see a strong positive correlation between a couple of our criteria. And that indicates that we can actually reduce the number of criteria that we're including in this decision analysis. So, for example, greenhouse gas emissions and air pollution, we actually really expect those things to be very similar. Air pollution and fatalities are like almost perfectly correlated, and that's because we got these fatality estimates from the IPCC, which estimated them from air pollution emissions, so that's a good sanity check. And we also see that water consumption and nuclear aversion are very highly correlated, and that's because of the high water use rates of nuclear power plants. So let's say that we wanted to actually use this in practice. We might say, okay, well, if I have a decision maker that really wants to get rid of nuclear power plants, and I really, really care about reducing water consumption, then I might use what I know about how these criteria are linked to talk in their language about what they want, but know that I actually indirectly get what I want due to how these 2 things are connected. And so then if we have the clear link between these lines, we know that there's one dominant portfolio. That's that red dot up there where my mouse is. And so that just tells us we have a single best portfolio that dominates all the others. But if we don't have a dominated portfolio, so in the pink box outline that I have, then you're going to get these sustainability trade-offs, right? So this is a Pareto frontier where you go from the best on greenhouse gas emissions to like the best on jobs. And so then we want to know, okay, well, what are the trade-offs at the system level for these 2 different energy futures? So this is kind of where the previous work stopped. And I graduated with my PhD, I moved to be a professor, and I'm thinking, okay, where do I go next? And one thing that I thought to myself was, how do the utility level or the national level sustainability trade-offs transfer to the local community? So this is just like a zoomed in version of the scatterplot matrix that we saw. And if I'm thinking about this air pollution emissions right here, have a nice little convenient green circle. So if I'm thinking about this air pollution emissions red dot, and I actually say, well, I really care about jobs in my region, and I want to move to this non-highlighted dot, what are the trade-offs that we're going to get? So where are those air pollution reductions happening in the region? Where are those jobs happening in the region? Are we creating new jobs, or are we actually creating an equal distribution of jobs? So that's kind of the motivation for me integrating this equality work. So now we're back at my decision analysis sustainable transition pyramid, and we're going to kind of talk about how I'm going to be integrating the equality part into the work that I'm doing. So when I think about equality, there are so many different definitions. So to make sure we're on the same page, let's talk about some of the different levels. So at the micro scale, this is when we really care about things like local environmental impacts. This might be the discrepancy between rural and urban areas in terms of the benefits that they get from electricity. This is a picture from sub-Saharan Africa, and you can see, like, in this rural area, they are literally under the power grid, so they've been excluded from these power lines that are actually going into the main city. So that's just one example. Then at the macro scale, that's like the global level, we think about extraction of materials in global waste streams. So in sub-Saharan Africa, we have a lot of mining, right? We are extracting those materials from there. We process it in the global north. We benefit economically from that development, and then we send all the trash back, right? So this is a huge global scale level of inequality in terms of who's actually benefiting from these materials and where the waste streams go. And then at the meso scale, those are going to be national issues such as unequal access to renewable technologies, air pollution effects, job distribution, and increasing electricity prices. And so it's kind of like if everybody in your community except for you was able to afford a solar panel on your house, right? That's like one example of a mesoscale issue. So I have decided to kind of start at the mesoscale for this work, and I'm really going to be focusing on national energy transition equality concerns. So the first one that I'm kind of thinking about are the pollution and health impacts and how those are distributed around the country. The next one is going to be employment. So within employment, there are two big equality concerns. First is for those losing their jobs, right? As we transition away from coal mining and things like that, who's actually losing their jobs and who's able to transition to a different sector of the electricity sector or a new type of job, who's getting retrained. And then the second part of employment is access to jobs. So historically, a lot of communities have actually been kept out of employment. And so we want to make sure that as we're transitioning, we're not only making sure that people who are currently employed aren't getting left behind, but that we are having equal distribution of jobs for a wide variety of the population. And then lastly, for the equality concerns, I'm thinking of this in terms of affordability. So this might be energy burden and energy costs. So for energy burden, that's how much of your income do you need to spend on actually meeting your energy needs? The energy cost is related, which is why they're kind of overlapping, but energy efficiency can also help bring down your energy costs and things like that. So those are the mesoscale equality concerns that I'm considering now in my current work. So, where are we looking at? Well, there's a ton of power plants around the US, right? Not all power plants are created equal. So we started off with just kind of getting a sense of the problem. So we have all these different power plants. There's coal plants and oil plants throughout the US. And we're going to do some emissions calculations. How are we going to do that, you might ask? Well, we have a very convenient equation right here. So we have the life cycle emissions estimate. So we have air pollution estimates over the lifetime of the plant. And the emissions calculation, where EG is the air pollution emissions associated with generation, is equal to the sum of the emissions factor, which is the air pollution unit per unit of energy. That would be like the CO2 emissions per kilowatt hour or per megawatt hour of that specific power plant. The UG is going to be the power plant generation, and K is going to be the scaling factor, which can account for the different efficiency of power plants. So the emissions factors come from like the literature, and they have their own emissions efficiencies associated with that. And then our K scaling factor is how we're going to accommodate for each of those different power plants I showed, having different efficiency levels. So here is a preliminary map of where we see the most SOX emissions around the country. And it's really interesting that we see there are really 9 power plants in the US that are the largest emitters, over 10 teragrams of SOX. And so when we're thinking about national electricity transitions, when we're saying we want to retire coal plants, we really want to make sure that we're focusing on our largest emitters. And we see that there's a lot in the Southeast, Midwest, and then kind of in that Northwest region. But you might also say, well, there's not just one national electricity policy maker, because we have these different independent system operators and utilities around the country. So which utilities should we focus on trying to get to change their policies? So here is a utility map where we actually looked at the different SOX by the different ISOs, or independent system operators. And we can actually see that some of the largest emissions are coming from the Meso region in the Midwest. And so just kind of thinking about how can we make sure that we are incentivizing wind or hydro or solar in that region, and in a way to make sure that we're retiring some of those large emitters as early as possible. Then if we say, okay, well, where do we go after? If Meso solves all their issues, then we might look at CAISO and PJM. Now, I will say that CAISO just has a ton of electricity generation. So efficiency combined with moving the power plants would also really help there. And then we have the Southwest Power Pool in NYISO, which is the New York Independent System Operator. And then lastly, our focus would be on ISO New England and ERCOT. So this just kind of helps inform like where the problem is and how the distributions of emissions change based on the different system operators and utilities in the US. Now, I know that there are some blank, and so that's kind of where we would need to think about like different strategies, because they don't necessarily have that energy market in some of my blank areas, but that's another issue for another PowerPoint. And so then we also have like, how do jobs link to these different technologies? So here we have a bar chart of the jobs on the y-axis. The x-axis is the different technologies. The blue represents electricity generation jobs, and the black represents jobs associated with the fuel sector. So for example, the blue jobs are represented just from like construction of power plants and generating electricity from them. And the black would be like drilling for oil, fracking, etc. So we see that when we put some of these technologies side by side, we really are going to have to think creatively about how we can replace some of these jobs. Because, for example, if we just get rid of our oil plants, there are a few number of jobs that are associated with energy, but it's really this deep decarbonization of the whole sector to get rid of the fuels that is really going to impact the jobs. So as we move towards deep decarbonization, then we really have to think about jobs there. And then we see that for coal and for nuclear, we actually see a similar number of jobs in terms of electricity generation, but coal is a bit higher due to its coal mining and fuel extraction. So kind of thinking about the differences there is one thing that we are trying to take into account, because it's not just having a job, but it's the quality of a job. So we talked about kind of like losing jobs, but there's also access concerns stemming from job distribution. And it's because of these historical employment discrepancies. So the bar chart is representing the percent of the workforce, and the striped bars are the energy workforce, and the green bars are of the overall economy. So with women, we see that less than 30% of women are employed in the energy workforce, but women actually represent almost 50% of the employment in the overall sector, in the overall employment sector. And veterans are actually, they actually represent a large proportion of the energy workforce compared to the overall economy. We see that there's about like a 3% difference between Hispanic and Latino/Latina/Latinx in employment, and then African Americans have also been largely kept out of this energy sector compared to the overall economy. So when we're thinking about this distribution of jobs, we want to also make sure that we are not perpetuating social imbalance as we're moving forward and thinking about energy transitions. And then comes in the affordability piece. So with our energy burden, how we're thinking about that is how much do you actually spend on your energy expenditure relative to your household income. So right now for energy expenditure, we're looking at states' average monthly electricity bills, and we're looking at the total households within a tract. And then for the median household income, we're looking at the households within a census tract. So to kind of help you visualize this, this is a map of the US, and A red square indicates, a red highlight indicates that the energy burden is more than 6%. So we see that Alabama actually has like a very high count of energy burden populations. So Alabama is kind of like right over here. Whoops. And we see some in Texas and some in New Mexico. But we're looking at the census tract level. It's very highly detailed. And one of the things that we're not capturing are the differences between different racial and ethnic groups. So we actually have another map where we're looking at energy burden as like racial distinctions. And we find that in the Southeast, we see a lot of African American and American natives, or Native Americans, sorry, in the Southeast having energy burden. In like Texas, we have a large Hispanic population over here. And we also see a large African American population having energy burden. So trying to think about different policy solutions for different groups based on their different cultures is something that we also want to take into account. But where we're starting is how can we expect the distribution of energy burden and energy costs to change as we move forward with energy transitions? So where are we making those jobs? Where are we reducing prices? Where do we actually increase prices based on, let's say, high offshore wind technology, high cost offshore wind technology or a nuclear technology and things like that. So to sum it up, for the future framework, I'm actually just changing 2 of those bubbles that I had showed you before. So we still have resources and nuclear outages, and we still are going to be looking at different generation types and costs. But the main thing that we are going to do is change our energy system optimization model to incorporate spatial distributions around the country. So where would those power plants be built? Which ones would be retired? We're going to output a spatial distribution of capacity mixes and expected energy contributions by technology and power plant locations. Then we're going to actually calculate the distribution of jobs, pollution, and energy costs around the US. And then we're going to run through our sustainability model again to get a better sense about how equality concerns and how energy justice concerns would be impacted by energy transitions in the US. So to conclude, the information that I presented to you here illustrates how investment decisions change under different objectives, and future work is going to look at the spatial distribution of jobs, costs, and technology investments. I really hope that if you leave with nothing else, that you see that there is a large need for trade-off models, because there's so many objectives in power system expansion decisions, and our work here is really designed to help regions highlight which strategies will assist them in reaching their ultimate sustainability goals and understanding the trade-offs that they're making. So I would like to thank you all for listening. I want to acknowledge my PhD student, Andrew Jones, who actually made the energy poverty maps and is doing really great work in energy poverty. And this is my contact information and the reference to the paper that I had shown. So thank you very much for listening.
And if you guys have any questions, feel free to use the Q&A tab now on the portal to ask any.
Okay, and can you guys hear me?
Yep.
Yep. Okay, all right, great. So Dr. Nock, thanks so much for an excellent talk. I know as an energy modeler, it definitely gives me a lot to think about. So what I'll do is as the questions come up, I'll kind of read them off and give you a chance to respond. But maybe while we're waiting, I had several small questions, but I guess the really big one, and the thing that interests me a lot is on the equality front, which I've, as a modeler, I've probably spent the least amount of time thinking about, unfortunately. And what strikes me is that there's going to be, no matter what we do, if we really are serious about decarbonization, like there's going to be winners or losers, right? But
right.
I think when we think about equity, we want to make sure that we have to have a thought process about like who are the winners and losers, and some moral judgment about is it fair? And so to me, it seems like there has to be, I mean, do you have to, in this work, develop clear criteria about what sort of groups you're tracking? So I just started to make a list of, things that would be of concern to me, like, is there a disproportionate impact based on race, gender, ethnicity, income, and also political power? I mean, you might have a well-mixed group of people, but if they're marginalized and they have no real ability to politically mobilize, then it's easier to sort of ignore their concerns. But I'm wondering, like, in this work, do you have to develop clear criteria about what groups you're trying to track to determine what's equitable?
Right. And so that's why we had made these maps to kind of get a sense of the problem, right? So when I'm thinking about what's equitable, one thing that kind of jumps out to me is that there's a lot of red on this map, right? And so when I'm thinking about trying to make sure that I'm equitably reducing energy burden among different groups, that I'm not only focusing on one. So for example, in New England, they actually have a very high level of energy costs. They actually have one of the highest prices for electricity, but we don't see that many instances of energy burden in here. And that's because the median income is actually much higher than in the South, right? And so when I'm thinking about low cost technologies, energy efficiency measures, we can actually see that one of the places that's being left behind is in the South and some parts in this Midwest region. So one of the things that we're actually thinking that this could help with is a preemptive tool to say who might get left behind and who might try to impede energy transitions, right? Because right now, we're kind of retroactively trying to do job retraining because now people are mad. We have coal miners that are really upset. We have people with the fracking that are really upset. And so we were thinking that there's a need for a model that can actually look in advance and say who might be upset, and let's go see if we can actually get their input and get their concerns and make sure that they feel that their concerns are heard and what types of jobs they might want. So when I kind of showed the job bar chart of the fuels jobs versus the electricity generation jobs, I mean, a coal miner might not want to do solar panel construction. Those are two totally different skill sets, right? And so kind of making sure that they're included in the conversation is one thing that would be important. When I'm thinking about actually measuring distribution, I actually use what I call the Gini Coefficient. The Gini Coefficient is a measure of, people typically use it for income inequality as a distribution around society. And what we are going to do is we're going to apply this to jobs and to energy burden. So if we are kind of looking at the nation as a whole and we're saying, okay, well, the Gini Coefficient is at its theoretical maximum of 1, where it's totally unequal, we're not the same. And then if we do all this energy transition and we have one path that gets us to 0.8, so we're getting closer to 0, which is better for the Gini, and there's another one that gets us to 0.5, maybe we should do the one that's at the 0.5. And let's see how much we win and lose on CO2 emissions, for example.
Okay, very interesting. Great, thank you. Looks like we've got some questions here, so I'm just gonna kind of queue them up as they've come in. So the first question is, in slide 32, it says the job numbers are based on total generation or unit generation.
2. This is from the Energy Employment Report. So they actually do a survey of, I think, 30,000 people, and they get information from the companies, and so then they get it to people, the jobs in people.
Okay, so it looks like this is maybe total number of people. It's not normalized per gigawatt or.
No, I don't think so.
Okay. Second question is, how should wages play in with number and type of jobs? So not just the number of jobs, but also the wage level. Right.
So that goes back into the quality of the job, right? There's also other concerns that we need to consider, like for solar companies, you have to travel a lot. With coal, you get to like have like your community, you get to like live there. So the jobs is still at the beginning. We are right now just looking at the number of jobs, and we're kind of thinking through the different methodologies there. As you can probably imagine, it's very hard to get at the quality level from a very like top-down perspective. So one of the things that I like to do in my work is just frame the problem and then try to use that as like a springboard for more research and more analysis. So I think those are great questions. I don't have all the answers because I'm not a jobs expert. I'm a modeler. So yeah, I will not claim to be an employment expert, but we are trying to work with a company to actually do like another survey in addition to like using the results from this one. And but that's kind of like a step 4 or 5 in my work.
Gotcha. Okay. Okay. And then another question was about the nuclear inclusion. So the comment is, it's interesting that nuclear inclusion in the energy mix leads to one of the highest performing portfolios, and similarly, nuclear aversion plays such a large role in the lowering of the ranked portfolios. What can or should, if anything, be done to address the public policymakers' aversion to nuclear energy? And I might just add to that, I had a little bit of confusion. I just wasn't sure exactly how to interpret the hashed bars for nuclear aversion on the end. Is it making things, so when you remove nuclear, it's actually making the results better? And then is there some sort of interplay between, like if you exclude nuclear, does it change LCOE at the same time, and how does that affect the bar? So
okay, so the red striped bar is saying if there's no nuclear, that's really good, like you get a sustainability value of 1, and if there's a ton of nuclear, then you get a 0. So you have to remember that I'm normalizing only for the portfolios in my set. So the highest nuclear capacity portfolio, which I think had like 9,000 megawatts, gets a score of 0 because that's the highest one. And then the one with the lowest value of nuclear, which are going to be 0, I retired it all, that gets a sustainability score of 1. So that's why you have like this 2 and 3 having this really long bar, because it's a value of 1. So when we have like issues like Chernobyl and Fukushima, for example, we see huge shifts in perception about nuclear. Like everybody wants it gone. Like that's what you saw with Germany. And so we added this in as like a kind of like a, what if an extreme event happens as we're doing this transition? So like, people have like really high risk aversion, especially in the electricity sector, because technologies are around for so long. So this was just to get a sense of if we have an extreme event in the middle of this transition, because my portfolios are assuming that you're doing this transition for 20 years, right? Then what would be one of the, like, how would people change? One thing I will show, sorry, I have to go to a different PowerPoint. Let me see. I'll stop sharing so you guys don't have to watch me. I actually did look at how would we change this if people's preferences for nuclear aversion changed over time. And so I actually have a nice graph that is, I will show you that. Okay. Okay, so we have the sustainability score here. So higher is better. And we have our nuclear aversion scaling coefficient. So if you have a 0, that means you don't care at all about nuclear. And then if you're at like 0.8, that means that you just 80% of what you care about, you just want nuclear gone. You don't care about anything else, really. So this square dotted line is portfolio 9, which is that really high level of nuclear and wind. And then the portfolio 4 is the high nuclear case. And then the orange ones are going to be the ones where we retired nuclear completely. So as the preference for just retiring nuclear gets stronger, so as you're moving to the right, we see that portfolio 9 is slowly decreasing over time. But when you get to, let's just say like 30% of all you care about is retiring nuclear, you start to see these ones where we've completely gotten rid of nuclear. So that's like Germany, for example, rise to the top. And these ones where you've kept nuclear on board kind of fall to the bottom. And you get these 4 different groupings of portfolios. So one thing that we kind of use this to think about is if we think that we're going to run the risk of another nuclear event happening in the future, and we think that decision makers are just going to want to retire it, then maybe we don't do portfolio 9, because in the future it would just fall right to the bottom. And maybe we should stick in this second grouping where we can actually just compromise. So a lot of the trade-off analysis is kind of thinking about what are those compromises going to be. So this black line here is the base case. So you actually see the base case falls in this middle track. So even though it's kind of at the towards the bottom in the, you know, we don't care at all about we don't care about nuclear, as this preference for aversion gets stronger, if we wanted to still keep on our base nuclear, we should stay here. And it's easier to shift from these to these than it is to go from like this pink line back all the way up to the top. I don't hear you, Joe. Maybe you're muted still.
Sorry. So there's some more questions coming in. I'm going to go slightly out of order because it looks like there's a sort of a follow-up question about nuclear, and then I'll get to the other question. But someone said, I recall you saying that some of the portfolios have plans to phase out nuclear after they phase out oil. Given that nuclear has low operating costs and high baseload power, wouldn't it be worth it to keep the plants in the future rather than dismantle them when we've reached a more sustainable energy sector?
So it's saying to dismantle oil first and then go to nuclear? Is that
I think they're saying instead of, given that nuclear has low operating costs and higher baseload power, wouldn't it be worth to keep the plants in the future rather than dismantle them once we've reached a more sustainable energy sector?
Yeah, so I agree with that statement. I think that because of the large baseload power, I mean, nuclear over its lifetime has the lower emissions. I mean, wind and solar, you have to replace them often. They have a lower lifetime and a lower lifespan. And silicone for solar is actually very intensive for making, it's very carbon intensive is one thing I've learned from like the fixed values of that. So I personally think that it's good to keep the base load levels going as long as you can as you transition. One of the risks in New England was the thought of using natural gas as like a gateway to renewables, which is a challenge, right? Because it does have emissions associated with it. So I agree with the person with the question.
Okay. Okay, and then the next question is, an increasing percentage of the greenhouse gas emissions is coming from developing nations for whom fossil fuel use is often the fastest and cheapest way to achieve rapid industrialization and increase prosperity. What's your perspective on how we can help developing nations industrialize while minimizing global greenhouse gas emissions?
Yeah, so I actually had a meeting with a bunch of stakeholders in Ghana. And when you look at the emissions relatively, they're actually not as large as what we're still polluting. So I have like a hard time, going to these other countries and like telling them to lower their emissions because they want the development. They want the industrialization. They want the economic benefits, right? And it's really, really hard to do that if you have intermittent technologies. So, for example, like with solar, right, with the batteries, they have actually talked about how a lot of the solar home systems are abandoned once people have to replace the battery because the upfront cost is so high. And when you're thinking about the way that they're using these batteries and they have to replace them every 3 to 5 years, like who am I to go in and tell them like emissions are more important than economic development, right? So I think that taking that Western view is into developing countries is a really big challenge, and it's something that I caution people against because, you know, like why should they pay for what we cause in the developed world? Now, I definitely think that like air pollution emissions are a big problem, but I also recognize that like jobs and employment and economic development, like people are when I went to Ghana, we're talking about wanting to bring car manufacturing into the country. And they couldn't get like Mercedes-Benz or Toyota to build a large factory because they don't have a large consistent supply of electricity. And so even though they were saying they didn't want coal plants, they were saying like, why can't we have nuclear? Why can't we have like methane from our lakes, right? That type of thing. And so I think that making sure that we're balancing like economic development and equality and jobs and air pollution is going to be a big challenge moving forward. But that's why I love trade-off analysis.
And it seems like your analytical framework accounts for that. That if you took your model and you built one for Ghana, you have these weighting functions, so you could weight jobs and other things more highly, and environmental impacts less, and still come out with the sort of solutions that the stakeholders are looking for.
Right. Yeah.
Okay. I'm aware of the fact we're past 1 o'clock, so maybe just one more question. There's a question about do you plan to consider transmission and distribution investments as well, as they have significant impacts to cost of service as well as equality?
Yeah, so we are going to include transmission in the new spatial distribution modeling. We're looking at using NREL's Reeves model, which actually can incorporate transmission and distribution constraints there. And thinking about if we allow for like transmission expansion, how does that actually change emissions throughout the nation, as opposed to like not allowing for transmission expansion. So like if for some reason the ISOs decided to like not cooperate as much with each other.
Okay, and then I'm sorry, there was a follow-up part of the question, demand side investments as well.
Right now, I'm not looking at demand side investments because I'm modeling it from the view of like a central decision maker. And when you get into the demand side investments, I think that would mean that I would need to model more of the like household individual level, where like I've aggregated the entire ISO to one electricity profile. So, I already have uncertainty there. And when you start to get to this individual household level, you get into more uncertainty, which when you combine it, it kind of mutes out that effect a little bit.
Gotcha. Okay, well, I really appreciate you taking the time not only to give the talk, but answer all of our questions. Adi or Martina, I want to give you an opportunity. Is there anything you wanted to say before we close out?
Yeah, I wanted to first of all thank Dr. Nock for presenting. This would usually be the part where you hear applause, but we would also like to thank the audience for joining SEC's first ever webinar. If you would like to learn more about Dr. Nock's work, you can visit her blog at destenienock5.wixsite.com. And if you're interested in learning more about our organization and our efforts, be sure to check out our website at ncsuenergyclub.org. I don't know if Adi wanted anything else to add, but if not, thank you all for joining us and have a great Friday.
Thank you.
Thanks so much.
Thanks, Joe.
All right, take care.
See ya.
See ya.